Hello, class. Today, we're going to dive into a topic that's fundamental for handling very large and very small numbers in science and mathematics. We'll be focusing on operations with numbers in the form a times 10 to the power of k. This is commonly known as scientific notation or standard index form. By the end of today's lesson, you will be able to understand and use scientific notation and perform all four basic arithmetic operations: multiplication, division, addition, and subtraction, with numbers written in this form. First, let's break down the notation itself. A number in scientific notation is expressed as a product of two parts, a number a and a power of 10. The number a must be greater than or equal to 1 and less than 10. The exponent, k, must be an integer, which means it can be positive, negative, or 0. The symbol k is just a mathematical shorthand for saying k is an integer. This form is incredibly useful. For example, the distance to the sun is about 150,000 meters. In scientific notation, we can write that much more concisely as 1.5 times 10 to the power of 11 meters. It's a much cleaner way to handle these huge numbers. Let's begin with our first operation, multiplication. Our goal in this section is to learn how to multiply two numbers that are both in scientific notation. The rule is quite straightforward. You multiply the a parts of the numbers together, and you multiply the powers of 10 together. When you multiply powers with the same base, you add their exponents. So for two numbers a times 10 to the k and b times 10 to the m, their product is a times b times 10 to the power of k plus m. Let's work through an example from your notes. We want to calculate 3 times 10 to the 7th, multiplied by 4 times 10 to the negative third. First, we group the a parts and the power of 10 parts. Using the commutative property of multiplication, we can reorder this to group the coefficients 3 and 4, and the powers of 10, 10 to the 7th, and 10 to the negative third. Now we perform the two separate multiplications. 3 times 4 is 12. For the powers of 10, we add the exponents. 7 plus negative 3 is 4. So we have 12 times 10 to the fourth. Now take a moment to think. Is this our final answer? Is it in proper scientific notation? The answer is no. Remember, the a part must be between 1 and 10. Our a part is 12, which is too large. We need to adjust it. We can write 12 in scientific notation as 1.2 times 10 to the power of 1. So we replace 12 with that, giving us 1.2 times 10 to the 1, all times 10 to the 4. Now we add the exponents again. 1 plus 4 is 5. Our final correct answer is 1.2 times 10 to the fifth. So we've successfully multiplied two numbers in scientific notation and ensured the result was in the correct form. We achieved our objective for this section. Next up is division. The principle is very similar to multiplication. Here, our goal is to divide one number in scientific notation by another. To divide, you divide the a parts of the numbers, and you divide the powers of 10. When you divide powers with the same base, you subtract the exponents. So for a times 10 to the k divided by b times 10 to the m, the result is a divided by b times 10 to the power of k minus m. Let's look at the second worked example. We need to calculate 3 times 10 to the 7th divided by 4 times 10 to the negative second. Again, we'll split the problem into two parts, the coefficients and the powers of 10. This is equivalent to the fraction 3 over 4, multiplied by the fraction 10 to the 7th over 10 to the negative second. Now let's calculate each part. 3 divided by 4 is 0.75. For the powers of 10, we subtract the exponents. Be careful here. It's 7 minus negative 2. Subtracting a negative is the same as adding, so 7 plus 2 is 9. This gives us 0.75 times 10 to the ninth. Once again, let's check if our answer is in proper scientific notation. Is 0.75 between 1 and 10? No, it's too small. We need to adjust it. We can write 0.75 as 7.5 times 10 to the power of negative 1. Substituting this back in, we get 7.5 times 10 to the negative 1, all times 10 to the 9. Adding the exponents, negative 1 plus 9 gives us 8. Our final answer is 7.5 times 10 to the 8th. Excellent. We've now covered division and have met our objective for this part of the lesson. Now for something a little different, addition and subtraction. Our goal now is to learn the method for adding and subtracting numbers in this form. Unlike multiplication and division, we can't just combine the parts directly. There's a crucial first step. The key rule for addition and subtraction is that the exponents on the powers of 10 must be identical. If they aren't, you must change one of the numbers so that they match. Think of it like combining like terms in algebra. You can add 3x and 4x to get 7x, but you can't directly add 3x and 4y. Here, the 10 to the power of k part is like the variable. Let's try this example. 3.2 times 10 to the 19th plus 4.5 times 10 to the 20th. Notice the exponents are different, 19 and 20. We need to make them the same. It's usually easiest to convert the smaller power to match the larger one. We want to rewrite 3.2 times 10 to the 19th as something times 10 to the 20th. To go from 10 to the 19th to 10 to the 20th, we multiply by 10. To keep the number's value the same, we must also divide the coefficient by 10. So 3.2 becomes 0.32. This gives us 0.32 times 10 to the 20th. Now that the exponents match, we can perform the addition. We can factor out the common term, 10 to the 20th. This leaves us with 0.32 plus 4.5 inside the parentheses, all multiplied by 10 to the 20th. Adding the coefficients gives 4.82. So the answer is 4.82 times 10 to the 20th. Let's check. Is 4.82 between 1 and 10? Yes, it is. So our answer is in correct standard form. The same exact principle applies to subtraction. Let's do a quick subtraction example. Consider 8 times 10 to the 5th minus 4 times 10 to the 4th. Again, the exponents are different. We'll convert the smaller one, 10 to the 4th, to match the larger one, 10 to the 5th. 4 times 10 to the 4th is the same as 0.4 times 10 to the 5th. Now we have 8 times 10 to the 5th minus 0.4 times 10 to the 5th. We subtract the coefficients. 8 minus 0.4 is 7.6. The result is 7.6 times 10 to the 5th, which is in standard form. We have now successfully covered addition and subtraction, meeting our final objective for the core operations. To wrap up, let's see how these operations are used in a practical, real-world context. Our final goal is to apply what we've learned to solve a word problem. Here's our problem. We know that 12 grams of carbon contain approximately 6.02 times 10 to the 23rd atoms. This large number is known as Avogadro's number. We want to find the mass of a single carbon atom. To find the mass of one atom, we need to divide the total mass by the total number of atoms. This is a division problem. So we set up our calculation. 12 grams divided by 6.02 times 10 to the 23rd. To use our division rule, we should first write 12 in scientific notation. 12 is equal to 1.2 times 10 to the power of 1. So our division becomes 1.2 times 10 to the 1 divided by 6.02 times 10 to the 23rd. Now we apply the division rule we learned earlier. We divide the coefficients. 1.2 divided by 6.02 is approximately 0.199. And we subtract the exponents. 1 minus 23 is negative 22. This gives us about 0.199 times 10 to the negative 22. Is this our final answer? Let's check the format. The number 0.199 is not in standard form. We rewrite it as 1.99 times 10 to the negative 1. Combining this with our power of 10, we add the exponents. Negative 1 plus negative 22 is negative 23. So the mass of a single carbon atom is approximately 1.99 times 10 to the negative 23 grams. This is an incredibly small number, which is exactly why scientific notation is so essential in fields like chemistry and physics. Today, we've thoroughly covered how to perform all 4 basic arithmetic operations with numbers in scientific notation. We learned to multiply and divide by handling the coefficients and exponents separately, and to add and subtract by first making the exponents equal. Finally, we saw how these skills apply to real-world calculations. Well done.